just test it out here. I think it's working now.
Yes.
It's recording.
Yeah, it is. Okay, great.
Hi, Pat.
Hi, Bryce. Hi, Ian.
Hi, Pat.
Therese.
Hello, all.
Well, it's really nice that we're able to help you out this morning, Pat.
Yes.
He was going to be bored stiff and visualizing an exam electronically.
This is much better.
I guess we can wait a little bit.
No, just got a couple minutes.
Sounds good. Yeah, that's great.
Yeah, Sebastian's not coming because there's something going on at school and Florian is turning 4. I think of this kid Florian as being a 1-year-old.
Yep, that's what he told me. So he's one of the people who wants the recording. This is a early morning for me.
I was up at 6 to do my slides and recording for my grad course. Actually, it worked a heck of a lot better then than later in the day.
Nice.
I'm with you, Bryce. This is an ungodly time.
So, Pat, are you back in your office or is this at home?
No, this is my office in my basement. I spend way too much time in this room these days.
Got it.
Teaching and working from here.
Well, it's looking a little better than my basement office.
Yeah.
Oh, and Pat, you've got the whiteboard behind you.
Yes. Yeah.
I know Jorg had that. It's a good idea.
That's what I teach on.
If I'd if I figured that out, I probably would have done it that way rather than trying to record.
Looks like Therese also wants to show off her backboard.
Of course, but I am also cheating because I'm at the university, actually.
Oh, okay.
So it's not my whiteboard.
Are you going in, Teresa?
I am going in. I have children at home doing school from home, and it's just driving me crazy. I can't get anything done while they're doing stuff. And we don't have a basement that I could hide in and not hear them.
Yeah. And my children are doing school at school these days. Thank you.
Mine used to, and then one of them got rather panicky and said she would like to do it from home, so she's doing it from home.
Yeah.
Well, should we begin or?
Yeah, do we lose time? Oh, we got a bunch of other people? Yeah. Oh, Meng's here. Good. Naomi.
Oh.
All right, cool. Let's.
Okay, so let me just introduce so then I know the cue to pause to start the recording. So,
okay, sure.
Hi everyone, welcome to the Algorithms and Complexity seminar. And today we're happy to have our own Bryce that will talk about lazy search trees. So take it away, Bryce.
All right, just gotta have my screen shared here. Okay. How does that look for everyone?
Looks great.
Looks great. All right. All right, guys. So my talk is called Lazy Search Trees. And this is joint work with Sebastian Wild, who was a postdoc here at Waterloo, now has a faculty position at University of Liverpool. And this actually just came on archive yesterday. It was accepted for publication at Fox. And let's get started. All right, so what's the problem description? Problem description is to essentially support the operations of a binary search tree. So this includes for queries, I have, you can do rank queries, which is to say, given a key K, I want to find how many elements represented in the data set are less than or equal to K. I want to be able to select the rth smallest element, determine if a particular element K is represented in the set, find the largest element that compares smaller than a key K. Similarly, successor, and we want to be able to extract the minimum or just find the minimum, find the maximum. And for dynamic updates, we will allow the insertions of new keys. We'll make the delete operation have a pointer to the particular key. And to get the pointer, we could always just do a membership query and hold on to where that element exists in memory. And then we'll also allow a change key operation where we have a pointer to an element again, and we change the key to a new key, K prime. And we'll support splitting at a rank R so that returns two data structures the same form that have all elements less than or equal to R, and then all elements greater than R. And then finally, we'll support the merge of two such data structures. And we will make this in the binary search tree sense of all the elements of T1 being less than or equal to the elements of T2. And just a note here, I am allowing duplicate elements, but in terms of theory, this really is not any different than making elements unique, because I can always just say put the insertion time, couple that with the key, in which case I can use that as a tiebreaker. But it should be possible to, from an implementation standpoint, when I actually describe the data structure, to allow keys of the same value. Okay, and we're going to call this the sorted dictionary problem. And the reason I'm calling it the sorted dictionary problem is because, so if you look at the standard dictionary problem, where we just require membership, insert, and delete operations, well, then you don't really need to maintain order. And that means that we can't, well, first off, we don't need to answer any of these other types of order-based queries. And if you don't need to maintain order, then in practice, this problem is solved. You can just use hashing, and that will be a constant time per operation solution. So we're going to focus on the maintenance of order. We will be using comparisons as our only way to differentiate keys. And we'll actually, we can work over the pointer machine. However, we will discuss our data structures with the ability to use arrays, just because this will lead to a more practical implementation. All right, so existing sorted dictionaries, basically any balanced binary search tree is a sorted dictionary. And in fact, prior to our work, it's pretty much the only sorted dictionary. So I just listed a few here. You can do ABL trees, you can do red-black trees, or also splay trees. And these balanced binary search trees are going to give you log n time per operation. So any of these operations, they all take log n time. Okay. However, there are some actual special theorems that are based for splay trees that allow you to get access times, particularly access times that are a little bit more efficient than what the other balanced binary search trees support. And these are amortized complexities with the splay tree, but just have a few of them listed here below. We can go over them quickly. So static optimality is this property that you can get this O log M over QI complexity. And that's when element I is accessed qi times in an access sequence of length m. So just kind of an example here, if you have an element that is accessed, say, a constant fraction of the number of times an access occurs, then it can actually get this access in constant time rather than paying log n time. So you can see how this might lead to more efficient runtimes if the elements are accessed in differing frequencies. Then we have the working set property, which says I can access element I in time log ti plus 1. And here ti is the number of items accessed since I was last accessed. So if I have a small number of elements I'm working through and I access them frequently in the same kind of time span, I can get faster than log n time per access. And then finally, we have the dynamic finger property. And this says that I can access element I in this log, the difference of j and I. And in this sense, I'm saying the number of keys between j and I, and I can do it in log the number of keys, and plus 1 in case the key is accessed again. And yeah, so yeah, those are the three kind of stronger theorems for splay trees with access times. So we can do a little bit better for some sort of dictionaries on accessing, and accessing can mean insertions or queries. Okay, so the most important, it's not a theorem, it's a conjecture. Conjecture based on splay trees is that actually splay trees are going to be constant competitive with any other binary search tree on any sufficiently long access sequence. So that means that on any access sequence of length, I think it's at least n or n log n, then splay trees are going to be able to perform that access sequence in time no worse than a constant factor of any other binary search tree. So this is a strong conjecture. And this has received quite a lot of attention. The original conjecture came from the original splay tree paper. This is Sleater-Tarjan in '85. And since then, there's been a lot of important work on this conjecture. This first result here from '89 actually gives some lower bounds on what a binary search tree, the time a binary search tree would be required to answer a particular access sequence. And this formalizes a model of what it means to be a binary search tree. Essentially, you have a left child, a right child, maybe a parent pointer, and you have rotations for updates. And once you formalize this computation model, you can then say things about how long certain access sequences must take. And then I have here the dynamic finger conjecture. It was originally a conjecture in the original splay tree paper, and it was proven, I guess this is 15 years later, in 2 SciComp papers. And then there was generalization of the working set and dynamic finger properties that I described on this previous slide to something called the unified bound. And similarly, there is a something called tangle trees by Eric Domain and colleagues in SciComp of 2007. And this actually gives something close to what was attempted to be proven for splay trees. And that is, it's a log n competitive binary search tree. And I think actually the tangle tree can potentially have like log n times log n operations. So it's actually not even necessarily optimal as a binary search tree. However, it does have this instance optimality property with just a log n factor. So it's kind of interesting. And then finally, another paper by Eric Domain and colleagues in Soda of 2009 gives kind of a geometric view of binary search tree access, and actually proposes a new data structure, new binary search tree. They kind of call it the greedy BST, which is also conjectured to be dynamically optimal. And yeah, this geometric view is kind of putting It's putting keys on one dimension and axes on the other, and allows you to kind of think about the problem geometrically. And there's even more papers. This topic just continues to get quite a lot of attention in the most important theoretical computer science venues. I won't go into all the details of these. Okay, so this is kind of the motivating, or at least one primary motivation behind the current project. So Dominic Optimality is talking about using binary search trees and how efficient can we make a binary search tree. But there's a few kind of obvious questions if you look at that on its face, which is, why are we only considering access instead of insert and query? And then why are we only considering binary search trees? So when looking at solutions, we care just about the actual solution to this sort of dictionary problem. We don't really care what the data structure itself is doing internally. And along those lines, we can differentiate between the insert and query operations. And that might allow us to kind of find these new areas of optimization, which can often be, well, we don't know until this work, but we'll see that it ends up being about as powerful as some of these specific theorems that have been proven for the splay tree. Okay, so motivation along these lines is if you look at the efficient priority queue literature. So Fibonacci heaps and its derivatives, they can offer improved runtimes if we restrict the operation set. Okay, so say I forget about all of these operations that require looking at particular points that are not just at the ends, the minimum and the maximum of the sequence. And instead, you just focus on returning the minimum or the maximum. Then suddenly I can get insertion in constant time instead of logarithmic time. I can get this change key in constant time as well, a decrease key. And I can even get this merge, which is more general than the previous merge. I can just merge two arbitrary Fibonacci min heaps in constant time. So there's kind of this optimization that seems like it might be possible to generalize to the sorted dictionary problem. So this is kind of a big motivation of our particular work. And the idea is, if we are able to generalize an efficient priority queue and support these queries for any rank, then we might be able to get a sorted dictionary with superior insertion times to a binary search tree. Binary search tree has to sort every element. Actually, go to the next slide here. So a binary search tree has to sort every element upon insertion. And sometimes this is really, it's doing unnecessary work. We don't really need to sort on insert. If we delay sorting until we actually need to sort the elements for a query, that might actually provide some more efficient behavior. And we'll get to this. And so there is some work that has kind of discussed a similar direction to this. And there's two main areas. The first is something called deferred data structures, and the other is dynamic online multiple selection. So we'll discuss this first area here real quick. And there's two papers that are relevant to our particular direction, research direction. And this first is a paper by Richard Karp and colleagues, SciComp of 88. And it shows that you can answer Q queries on a static set of n unsorted elements in n log q plus q log n time, and also that this is optimal. And then we have another paper that is some follow-up work on the same idea, which gives a kind of a semi-dynamic model. And I'll explain why I'm considering this semi-dynamic in the future. But we see here we can answer. I've made this q prime because now we're using a different variable than q. I'll use q in the rest of the talk, but q prime is going to also include these insertions and deletions. But it's still a very similar result. which is that I can answer Q prime queries, insertions, and deletions on an initial set of n naught unsorted elements in this n naught log Q prime plus Q prime log n naught. Okay, and let's talk about multiple selection. Some of you are probably already familiar with what the multiple selection problem is. Some of you may not be, and I'll just explain it here briefly. So the problem is that you're given an inserted array A, and you want to select elements of some, you want to select some set of ranks from this unsorted array A. So here I have an unsorted array. And for example, say I need to select the third smallest, the seventh smallest, and the 13th smallest element. Well, then I don't actually need to sort array A entirely. I just need to find kind of how elements, I need to fit these elements in between these ranks that I'm selecting so that I can prove these are indeed the correct ranks. Oh, sorry, these elements are satisfying the correct ranks that I'm looking for. So let's consider the complexity of such a algorithm, and we're going to let delta I be. Okay, I'll let delta I be the set of elements between each of these consecutive query ranks. We good? Okay, and then I will define this B to be the sum of the cardinalities of delta I log base 2 of n over cardinality delta I. This is something that's I'm pulling from multiple selection literature. However, I've redefined it in a certain way to make it so that it will generalize well with the rest of the data structure that we give in the talk. I am going to use this log base 2 when I want the output of the log to potentially be 0. Generally, in theoretical computer science, we consider the log function to have a minimum output of 1, even if its argument is 1. And so here I need something that's just purely mathematical. So I will let this output be 0 here. And so when I had defined this B in this certain way, it turns out that the complexity of multiple selection, so both there is a lower bound and a matching upper bound of theta B plus n. And this has actually been studied quite a bit. We can even get the number of comparisons. This is a comparison bound, really. We can get the number of comparisons to be B plus a lower order term. And so we can match optimal up to lower order terms. Okay, so there's kind of 2 papers in multiple selection literature that are relevant to the problem that we are discussing. This first one is a paper by Barbet et al. And Isa. And this says that we can actually perform the multiple selection when the ranks R1 through RQ are given online and in any order. We can do this just as efficiently as if we were given this information up front. And this was kind of extended to another somewhat dynamic, semi-dynamic model by Ray et al. Again in Journal of Discrete Algorithms, 2016. And it says that we can do online dynamic multiple selection in O of B plus n plus Q prime log n time. However, they make this pretty big assumption, which is that we assume every insertion is preceded by a search for the inserted element. Again, I'm having Q prime denote the number of search, insert, and delete operations. Okay, so let's consider all this previous work, and I'm going to pick some small. I've got some nitpicks on these previous publications that will I can kind of explain why they really are not going to be very general. All right, so the first issue is that when we have in deferred data structuring literature, we're not going to consider query ranks at all. So we get these bounds that are like n log q. And if you think about generalizing a efficient priority queue, n log q would be if you had a Fibonacci heap or a derivative data structure similar to a Fibonacci heap that had data that had operations in n log q time, where q is the number of extract minimums and n is the number of insertions. This is really not very good. Fibonacci heaps can actually support n plus q log n time for their particular set of operations. So we really would like to get some more fine-grained complexity results that allow much more optimization than just this this rough upper bound. And then in some of this other dynamic literature, which I've called semi-dynamic, we have this coupling between insert and query operations. So in both this this dynamic deferred data structuring paper and in this online dynamic multiple selection paper, we have queries, insertions, and deletions grouped in the same category, or here we have insertions must be preceded by a search. And so what this means is these results are only interesting if my initial set of elements is very large and the number of insertions and deletions are quite small. Because you see here, if I have a linear number of insertions, then this just becomes n log n. And that's just no different than a balanced binary search tree. And so you lose all of the extra optimization that we're trying to get. And the same thing here. Okay, so what will our model actually be? I have delayed the actual results of our paper until the very end of the talk. A little bit unusual, but that's because I need to give a formal statement of what our model is before those results quite make sense. Okay, so we will we'll follow something similar to multiple selection literature, and we're going to use this distribution, this partition of elements into gaps based on rank. And you can see here, this is similar to what I had before, but now I have these gaps, delta 1, delta 2, delta 3, delta 4. And all the elements in delta 1 are less than or equal to the elements in delta 2, and this so on and so forth. Okay, so now I can consider how this partition into gaps will change based on dynamic operations. If I insert an element into the gap, I must insert it into a place that respects the partition. So I have an example here. If I am inserting element 8, I find which gap it can fall into. In this case, it has to fall into gap delta 3. And I place it there. Voila. Not too difficult. All right, so how do queries work? So we're going to make queries be something similar to how multiple selection works again, but we can actually answer a much larger operation set. And let's just explain it once again with an example. So say I am looking for the rank of 5 compared with all the elements I'm representing in my data set. What's going to happen is I find this rank. So this is actually the answer to the query is 9. There are 9 elements less than or equal to 5 represented in my data set. And this will end up being the rank R I associate with the query. We'll get to this in the next slide or two. And what actually I'm going to do is I then take this rank R, find which gap it falls into, and then I split. I'm going to split the gap. So what I need to do is I need to define all the elements less than or equal to less than or equal to 5. All the elements greater than 5. This is my dividing line. I split the gap, and I now have 2 new gaps in place of the original gap. So that's how queries are going to work. And as promised, how do I choose this rank R? It's very simple. There's a little bit of a leeway in terms of the actual implementation, but essentially I want R to be kind of the rank that I need to recurse into in order to answer the query. So for rank queries and membership queries, R is just the rank of the queried element. And then for select, predecessor, successor, minimum, maximum queries, R is the rank of the element returned. Finally, splits, this is kind of a query and then an update. And R is just this argument R. Okay, so kind of the intuition of working with this model of partitioning into gaps. Well, first off, multiple selection fits pretty much directly into the framework. I haven't actually selected out the particular like the rank 3 element or the rank 9 element, but the point is that I still have this partition into gaps based on these ranks, and it turns out this is roughly same complexity of actually finding the individual elements of rank 3 and rank 9. Then I can actually get binary search trees in this model. Binary search trees are just each element is in its own gap. That means I must, I must have a sorted sequence as such. And finally, priority queues are an interesting case. And it turns out priority queues are actually going to correspond to a single gap delta 1. Okay, so I have all my elements here. They're just completely unsorted in this gap delta 1. Okay, so how can I perform an extract minimum query in our model? Well, it's quite simple. We first just perform this minimum query. The rank R is 1. We find the smallest element, put it here. And we've just swapped this with the 6 and the 1s get swapped. And I split it off, becomes a new gap. And then I now take this minimum, which must be in my gap delta 1 as a single element, and I remove it. I am now back to having a single gap. Okay, so our complexity goal. Recall that I have this measure from multiple selection literature is this sum I cardinality of delta I log base 2 n over cardinality of delta I. We'll be using this for a lot of the talk, so I'll just leave it up there so we don't forget what it is. Okay, so what is B actually doing? What characterizes the amount of information, really the amount of work that we've done present in the current gap partition. So we can see as an example here, and this is kind of obvious. If I have every element in its own gap, B is theta n log n, and that's logical because this is the complexity of multiple selection. If I'm sorting, clearly the complexity of sorting is n log n. And we can see how this works. Just each of these delta I, this is just going to be 1, and then log base 2 of n over 1. It's just log n for each of the individual elements. So we get n log n. Now, if I look at the priority queue, since I have all of the elements in one gap, there is actually no information present at all because I have not sorted anything at all. So actually I get B equals 0. And here I do need this this log base 2 to output 0 here. I have n over n, which is 1. So log base 2 of 1 is 0. Okay. Now, something interesting happens with multiple selection itself. When I have these more interesting gap partitions, I'm just going to get something that is between, it's going to be a super constant and O of n log q. So this is where we start to get kind of this n log q term coming back just organically in our model. And that's because I can bound the number of gaps with the number of queries. And then the worst case is that each gap, I should say, the most amount of information is present when each gap has the same size. And so that would mean each gap has size theta n over q. And if I go back to this B here, theta n over q, this is going to end up being log q. And this is the worst case you can show. Yeah, you can show this is the worst case. All right. Okay, so our goal is roughly going to be to achieve this B plus n complexity. So to match the optimal algorithm for multiple selection, and indeed multiple selection is a subcase of the operations we're performing. And so multiple selection is going to imply that this would be optimal. Important to note, however, is that since I am doing dynamic operations, I can create gaps, I can delete gaps, I can create elements and delete elements. I am going to need to look at something a little bit more fine-grained than this. I need to look at the per operation complexities, because this is not always going to be relevant by the time I get to the end. I could do a bunch of things, delete all the elements, and then there's nothing left. Okay, so let's go ahead and start getting into some high-level technical arguments. I'm really going to go into very few details about our construction itself. And that's just to try to make the talk to be high level and not overly filled with math. Okay, so I look at this B again, and I can consider how B changes in a per operation. Per operation. So if I insert into a gap delta I, then I can show that the change in B is going to be omega of log n over cardinality delta I. And I have proof by example here. I've actually,
Bryce, just one quick question.
Yeah.
That's talking about worst case, right? I mean,
correct.
that's when the insertion is in the center of the gap.
Yeah, so the model is actually not going to care where the element is inserted within the gap. It does care which gap it is inserted into, but it only actually cares about the cardinality of the gap.
Yeah.
But in general, our bounds are going to be over the worst case. Sometimes you can actually beat this if your insertions have a particular amount of structure.
Yeah. Okay.
Yeah. Okay. So I have our distribution into gaps right down here, and I've actually calculated B out exactly for this example. We have 3 log base 2, 16 over 3. There's 3 elements here, 9 elements here. 16 is n. Pretty straightforward. Okay. So what happens when I do my insert? This is just the example I had from earlier. Well, we see our 3 log 2 16 over 3 turns into 4 log base 2 16 over 4. Roughly, this is about the right amount, and I won't go into the details to prove that this is actually correct, but indeed it's a very easy proof. Okay, so this is actually quite good because we have pretty easy data structure that can just support this operation quite simply. So I can just store this set of gaps in a biased search tree where gap delta I gets weight cardinally of delta I. So here, if you're not familiar with biased search trees, I have just a small example to give you a rough idea of how this works. So I have these 2 nodes that will be of weight 3. And then I have 1 node that will be of weight 6. And the rough idea of a biased search tree is instead of every node having unit weight, I weight these nodes differently. And the goal will basically be to get the heavyweight nodes higher in the tree. And that will allow me to access them quicker. Okay. And what are we going to get from this? We'll get that access to gap delta I will actually take time O log n over cardinality of delta I. And this is the complexity we were going for based on our lemma 1. Just a real quick explanation for how this works. You take the sum of the weights in here in the numerator. Clearly the sum is going to be n because I have everything exactly how many elements are in it. And then the time to access a particular element is just log of that sum over the particular weight of that element. Okay, now let's consider how we can do queries. Okay, so I have a second lemma, which is that the change in B due to splitting a gap delta I into gaps of size Cx and x for C greater than or equal to 1 is omega x log C. So I've written this in this particular way because I at least originally found it to be the most succinct, cleanest way to describe this complexity. What you see here, I have this gap delta I. If I have the rank R going through delta I, I'll then create a new gap out of the elements smaller and the elements larger. And we can just do a quick proof as to why this is omega x log c. Again, this is actually not very hard, but I won't go through all the details. Basically, if we think about what this B is, this is an information theory bound. And you can prove this bound for multiple selection by doing these repeated single selections. And if you look at it here in this, this small example, we're basically trying to find the x largest elements out of a set of c plus 1x elements. And there are c plus 1x choose x many possible ways you can that you can choose these x largest elements. And as most of these information theory bounds go, I am only doing comparisons. So I have at most two options from any particular most two outcomes from any particular operation I do, which implies that I will be taking the binary logarithm of the number of possibilities. And in the worst case, I can always force your algorithm to take at least this time. And this is going to end up just being omega x log c. If you do the math in Stirling's approximation, it's pretty straightforward. Okay, so let's just take a brief pause here and consider how these complexity goals relate to the priority queue case. I find this case to be particularly illustrative. So as we recall, there's only one gap in the priority queue case. And that's going to mean that insertion is going to take log of n over, well, delta 1 is all of the elements. So it's just n over n, log n. Log 1. And this is just constant time. That's good. And also, removal of the minimum is going to have x equal to 1 and c to be theta n. And so we get that O of x log c is just O log n. That's exactly how these efficient priority queues work. Because I'm just, and so yeah, this kind of gives you this granular assessment of why these efficient priority queues can support the behavior they do. This is kind of what's going on beneath the surface. I just have a little diagram here. X is 1, Cx is n minus 1, which means c is n minus 1. So clearly c is theta n, and that's how we get to the log n. All right, so let's go back to this goal here of trying to get the splitting of gap delta I in this omega, in O of x log c. We'll look for the upper bound now, time. So it turns out this is actually the main technical challenge of our work. And I actually don't want to go into the details of how we do this. This is what makes our paper interesting. It's this kind of novel data structure problem. And unfortunately, the way we solve it, we have to add this log n term to insertion time. This is not ideal. And actually, since we've published this paper, we have been able to remove this additional factor using very different techniques. But yeah, for the Fox paper, we have this as part of the result. Okay, so now I can just go ahead and give you guys the promised results. There are a lot of them, and I'll even give some applications. So let's just go through them. So from a high level, I can show that over a sequence of n insertions and q unique queries, our performance is O of b, and then I can get n log n. I can also get n log q, but yeah, it's close to optimal in what our original complexity goal was. But we do have these kind of dangling factors, and here I just have q unique queries. That's just because for this upper bound, we need each operation to create a new gap. That's when the gaps make sense with this bound B. Okay, And yeah, as discussed earlier, yeah, this b plus n is a lower bound. So we're close to that lower bound. So we do have some interesting properties of the particular solution we developed. We developed this based on first principles, is really not based on really any other work. And it's primarily, our data structure is primarily array based. And that means that we only need this q or n pointers. And this is interesting for several reasons. If you consider a binary search tree, binary search trees have at least 2 pointers per node. And these pointer-based data structures are notoriously slow. Linked lists are far outperformed by arrays when that's possible to use an array. And if you look in priority queue literature, you have binary heaps end up being more performant than things like Fibonacci heaps, generally speaking, in practice. And that's often because they work off of an array. Arrays are just faster. So just a summary here, working off of arrays and limiting the pointers, it's going to decrease the constant factors. It'll improve memory usage, kind of obviously. You also get a lot better cache performance. And this can make a big difference in practice. Okay, and finally, our fourth high-level theorem is that we can actually use a splay tree as our biased search tree over the set of gaps. And if we do so, we get all of those efficient access theorems that I talked about in the beginning of the talk. So it's pretty interesting that although our direction that we take is orthogonal to the efficient access theorems that all that other previous literature is based, we can actually get them both simultaneously. And this is particularly powerful because we'll see here, I'll give some more specific examples, but our complexity is particularly good in terms of insertion complexity when the queries are non-uniformly distributed. It means I can leave these big chunks of unsorted data. Well, that's actually also the case that splay trees are good for. Splay trees are good at answering the queries when the queries are non-uniformly distributed. So although our data structure is meant for a larger amount of insertions and less queries, we both the splay tree and the lazy search tree are efficient when query distribution is non-uniform. Okay, and just these specific results, if I look at the individual complexities of the different operations, well, I can do this insertion in log n over cardinality delta I, as discussed, and I do have to add this slight log n factor, but it's an additive factor, and most often this is going to dominate, unless delta I is quite large. Okay, and so I can also do this query in almost optimal complexity. Actually, sorry, it is optimal. This log n ends up getting dominated if you look at the amortized cost of repeated splits. Each of those splits has to be on average at least log n in terms of their increase to b, and so this actually doesn't dominate. And the reason I need to pay this log n is because I actually do need to find the gap in which the query occurs. Okay, then I can support deletions. I do have to pay log n time for them, and this requires the pointer here. Otherwise, I need to do a query first, which could be more expensive than log n. I can support a change key operation. However, there are some caveats to this. So if I think about a priority queue, priority queues are only able to support decreased key or increased key. You can't just change all these keys arbitrarily. You'll run into lower bounds. So the way this works in our data structure is basically we want to be able to get this change key operation when the data structure is used as a priority queue. And so we have some kind of rough generalization of the change key operation. And I won't go into all the specifics, but basically, if I have this pointer to a key k here, I can move key k as long as its rank is going to go further towards the boundary of gap delta I, then I can actually configure whether this is going to be the boundary here, or even both. So I can go lower on the bottom half and increase the key on the top half. So we get some fairly general change key operation, but specifically this is there for the priority queue setting. And this does require everything to remain in the same gap. Otherwise, I have to just do a deletion and reinsertion at log n cost. Finally, okay, well, actually not finally, a few more. We can do a construction on an initial set of S elements in linear time, so we don't have to pay the extra log n factors. We can do a split in time equivalent to the query. That's because I have to first find a gap, split the gap, and then the bias search trees, we can just do splits in this log n time. And I can do a merge, as in binary search tree merge, again, just using the binary search tree, sorry, bias search tree merge. That's going to be, yeah, log n as a normal binary search tree. Okay. Yeah, I'll say the insert, delete, change key, construction, merge. They can be made worst case. However, our particular solution has both query and split amortized. And if we are using a splay tree as the data structure for the gaps, then the insert and the merge are going to be amortized time as well. And the amortized time here for our query operations is actually less big of a deal than you might think. You see here, if I'm splitting a gap, I can split a gap to size x and cx. This is going to take x log c time. If this gap delta I had linear size, then x can be linear. So x can be O of n, and so splitting this gap is going to take linear time. So this data structure is really relevant when we can afford to spend quite a lot of time on queries, and we're trying to get the insertions very fast. And so if we are going to have to spend linear time potentially on some queries, this amortization is really not as big of a deal, because it just means I might spend linear time when x is still small. But of course, on average, we do get this O of x log c behavior. Okay, now I can just discuss some brief applications here. So yeah, we can use the lazy search tree instead of using a binary search tree. And we can serve n insertions in q queries in O of n log q plus q log n time. So this is similar to what was shown in our related work. This is if we're just ignoring the query distribution. Query distribution, the worst case, gets this behavior. However, now we've completely generalized it to all operations of a binary search tree and decoupled these insertion and query operations. Well, this could be faster than a binary search tree if your number of queries is something like n to the c, where c is a half or a third or a fourth. Then we get a constant factor improvement. Or if q is much smaller, say log n or constant, then we get better runtimes. Okay, so I can kind of illustrate this non-uniformity in a particular type of operation sequence, which I do think is pretty interesting. So say I want to serve n insertions and q over k. I'll call these kind of range queries, where each query is for k consecutive keys. Well, then I have these q over k queries, but each query is for k keys. So q is the total number of keys requested. And now my complexity, instead of being n log q, it's now n log q over k. So assuming that this is the dominating term, which is likely for the type of operations or operation sequences we're going to consider, I'm essentially getting the k consecutive keys for free. Each consecutive key only costs log n time, as opposed to costing as opposed to increasing the complexity associated with each insert. it's kind of interesting. I will say, actually, we have implemented a rudimentary version of our data structure, and indeed, we can get faster runtimes in binary search trees, both when the number of queries are small and when I'm doing these kind of non-uniformly distributed queries. Okay, and then we can also our data structure can be used as a priority queue or a double-ended priority queue, and we'll get log n time insert and decrease key. We can also support all of the operations of a binary search tree, which is kind of interesting. This does affect future insertion and decrease key cost, however. So there is a trade-off here in terms of the actual complexities. You have to just look at the distribution into gaps. And as future work, we are trying to make this an even more general model where instead of looking at elements and putting them into gaps, we instead look at essentially, we want to look at the minimum partial order required to answer all of the queries. And if we can get complexity that is proportional to the complexity of the minimum partial order, then we don't have any trade-off. At the moment, we do have a trade-off here. And as described, we can also just support online dynamic multiple selection organically. Here, the dynamic part is more efficient than previous solutions. And we can also do some kind of a incremental quicksort. So it's actually ends up being pretty awesome. Our data structure can internally use, so basically what we do is we're going to store elements in these unsorted bags. And then we can actually use a form of quicksort to structure these bags as we access them, which is that we can select a random pivot and split based on random pivots internally. And so we can use what was the fastest sorting algorithm internally in our data structure. So this has good. It should mean that we possibly be more practical. And specifically, when you're looking at an incremental quicksort, you can return the q smallest elements in sorted order, and O of n log q plus n, n plus q log n. This is the same as q log q here. There's been some work to try to do this, and it's just another application that our single data structure can do all of these things. We could also even sort any part of an array in this optimal b plus n complexity, as long as our insertions are preceding our queries. Okay, and that is going to be it for lazy search trees. Are there any questions? Yeah, Pat?
Yeah, so I have a question about if you just blindly use this thing for order statistics, so insertion, deletion, and what is the median? So it's like a three-ended priority queue where the third end is the middle.
Sure.
So what happens then? Do you get constant time for those, the min, max, and median, or does the queries to the median cause the B to go up too much?
The queries, so it's actually interesting that you asked that, because that was the original inspiration for this research direction, was in fact looking at that exact operation sequence and wondering whether it was possible to see how efficient you could make it. And it does cause B to go up. You can do that operation sequence in n log q time, when q is the number of median queries, or q is the number of medians. Q can be any order statistic.
Yeah.
And yeah, this is a lower bound. In the worst case, it has to be n log q. So can't be as efficient as a priority queue, but it is something our data structure supports.
Yeah, I see. And I guess another obvious question is, so you complained about binary search trees being somehow this obsession that we have, but I guess for this particular thing, if you want to formalize it in terms of a binary search tree, it's a binary search tree where the nodes hold bags of consecutive elements, right?
Yes, definitely.
So I don't know. I don't know if there's any interesting Wilbur-style lower bounds you could prove there for sequences that don't just include searches.
Yeah. Yeah, I mean, you're right. It is still going to use the theory of binary search trees. And there is a reason why binary search trees are so important to theoretical computer science. There's no doubt about that. But I guess it's just interesting when you don't restrict elements to be sorted on insert, the kind of complexity gains you can realize. And yeah, there's still a lot of questions open in terms of, well, how optimal can you be when you are considering these insertion and query operations as separate operations rather than just considering the single access as dynamic optimality literature has done so far.
Yeah. Okay. Thanks.
Thank you. Any other questions? Or shall we conclude the talk?
So Bryce, maybe we can take the recording offline, and then if people have other questions, they can ask as well, I guess.
Sounds good. Let's see how I can do that.